This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Hello, welcome back to another lecture of construction history. Today we'll talk about the Byzantine and Romanesque methods of design and construction, and we'll look in particular at two devices that were developed especially during this period, which are the spherical dome and the groin vault. And we will begin by saying that this is a continuation of some of the techniques that we discussed for Roman building in Module 1. And so what we will be talking about today is fundamentally the influence that spread from the city of Byzantium, which is an old name for the city of Istanbul today, also known as Constantinople. And it is important to give some historical context about this. So towards the end of the Roman Empire, once Rome was sacked in the 5th century by the Visigoths, and during that period, in general, the empire started to become difficult to manage, and therefore the Romans divided their empire into two, the eastern and the western side. Now, the western side continued to be controlled by Rome, generally speaking, but the eastern side set up its own center here in Byzantium or Constantinople. Now, the Eastern Empire continued to prosper even more than the Western. They were subject to a lot of political turmoil, and so this political scenery also corresponds, of course, with the establishment of Christianity in Europe. And from Byzantium, due to its strategic position and also had its proximity with the East and other culture, we see the rising of a new style of architecture, which is ecclesiastical. It's an early Christian type of architecture. And from Byzantium, this tendency, these techniques and these influences eventually started to spread back to the West, and in particular in northern Italy and on the western shores of what is formerly known as Yugoslavia. So this is not just a story about Western architecture, but it's somehow how Eastern architectural influences also came to influence the West. So we will look at some examples. We will look at some techniques that were common in this period. We're looking at a period in time that is between 400 AD up until 1100 AD. And this normally is referred to as the period of Byzantine architecture or Romanesque architecture. So we'll look at some examples of construction, but also look at some examples of finished buildings, in particular in Constantinople, but also in northern Italy, in Ravenna, Venice, which is here, and Milan. Now, we spoke already about the Romans and their ability to build vaults, and without going back necessarily into that topic, I'd like to just remind you what the geometrical principles were that allowed this vault construction. Of course, the material was Roman concrete, or better still, opus cementitium, which is a forerunner of concrete of these days. But the geometrical device was this semicircular arch. So we find that most Roman architecture is based on alpha circle and an arch, a semicircular arch that can be left by itself as an arch structure, or it can be extruded along one direction and become a barrow vault, or you can have two arches that are used or oriented in with orthogonal direction and extruded in both directions, and in this case they generate what is known as the groin vault. Now the groin vault, unlike the barrow vault, has the advantage of discharging its loads only at 4 points rather than along the length of the vault itself. And then this method can be taken further by building a dome that is based on a semicircular profile again. And by revolving this profile at 360 degrees, it is possible to obtain a perfectly semi-spherical surface that can be used as a dome. Now the arch, of course, it's something that characterized Roman architecture. We saw already, we discussed about the Colosseum, for example. We saw how there was plenty of use of barrow vaults, but also, of course, of the arch itself. Now the arch is an interesting structure that, as you know, works only in compression. It is a series of stones cut typically with a trapezoidal profile known as voussoirs, and the top of the topmost of these voussoirs known as the crown or keystone. And the arrangement of these voussoirs is such that the weights and the forces of gravity transfer themselves from one voussoir to the next until they reach the base or the springing point of the arch, which is known as the abutment. And this is done in such a way that the loads always somehow remain within the center, or not too far from the center of gravity of every single voussoir, and they generate a phenomenon known as thrust, which is a lateral, it's a component of vertical and horizontal loads of compressive stresses that determine compressive stresses, and that can generate the possibility of a bursting of an arch. Now, when you have two arches that are side by side, these forces of thrust somehow balanced each other, and therefore the structure is not subject to this problem. Now, the same principle of the arch can be used by extruding that shape along one direction, in which case we create the barrow vault. This is the barrow vaults of the Colosseum. You can now recognize the Roman concrete sort of approach there with rubble and pozzolanic cement using it, but also you find there's plenty of barrow vaults that have been used using the technique of opus testatium, if you recall, kiln-dried bricks. Now, these techniques could also, of course, become spherical domes, and the Romans had developed methods of construction that relied on a very clever technique of construction joints known as ribs, as we said. And these ribs were mostly used to allow, for example, domes, like in this case, to be constructed in sections and then have some interlocking ribs along the meridians of the domes, through which continuity of the material, of concrete in this case, could be executed with more ease than if it was just a pure monolithic pour. Now, this is an important thing to say, because as we will see, somehow this idea of ribbing domes, it is also the historical precedent that will lead us to discuss the ribbed vaults of the Romanesque and of the Gothic methods of construction. Now, the Pantheon, of course, is the quintessential dome of Roman times, and you can recognize here in this picture its arrangement. You can see it's been devised as a series of meridians and longitude and parallels that sort of run in the orthogonal direction, and eventually they culminate at the top, which is left open, the oculus. But this is a semi-spherical dome that has been obtained with one of the methods we discussed before. And the section of the Pantheon will show you that there is an increase of section at its base that is also taking care of this additional thrust, which in this case is not on a plane or on a on a line, but it's on a radial arrangement that spreads at 360 degrees. So the phenomenon of the fundamental problem of stresses in domes is the fact that you have, yes, a compressive structure, but ultimately there is a transition point normally, which is known as the hoop, or a point from which compressive stresses can become tensional stresses, particularly at the base. So in other words, when you have vertical loads coming down from the top or the apex of a dome, once these stresses accumulate towards the bottom, they tend to develop some tensional stress at the ring that, like an arch tends to spread at the bottom, a dome that is spherical also tends to burst at the bottom. And so this bursting tendency creates tensional stresses. And these tensional stresses very often lead to some potential for development of cracks. And in fact, this is a picture of the so-called Tempio della Tossa in Rome that was surveyed by Piranesi. It's one of his famous representation of the antiquities of Rome. And you can see here how you have some Piranesi, the illustrator here, picks up the cracks in the vaults that are clearly along the meridians of this dome. Now, in fact, this is the problem also of the Pantheon, and it has been observed that the Pantheon has developed some cracking that are enlarging themselves towards the base of the dome. Now, with this, you understand why then the Romans had this ribbed approach, and this is the fundamental base we need to understand also to talk about what comes next, which is the Church of Hagia Sophia in Constantinople. And before doing that, we will see how somehow this church develops and applies some of the techniques of Roman construction, but it also takes it to another level. And the novelty of this church is the fact that it is a compound dome. So we described the Pantheon, for example, as a spherical dome, and we said how it has a tendency to burst, hence its notorious cracking at the base. But the Byzantine churches developed a new technique, which is a dome that sits on a portion of a lower dome, and this lower dome is somehow reduced to 4 triangular portions of a sphere, which are known as, then you can see one here, and the other 3 will be around, and these portions are known as the pendences. So the approach is here to create a dome that is spanning much more than you could achieve with a simple semi-spherical surface by having a compound profile that is half a dome almost, that is then surmounted by a smaller dome at the top. And this allowed the Byzantine builders to execute this magnificent church, which was then today is a mosque. It was eventually converted to a mosque in the 1400s. That still exists, still extant in Istanbul. And you can see here how the technique, there's a very large dome at the top. You can see the dome has a series of meridians that are expressed, which in fact are a series of arches that show how perhaps there was an understanding of the cracking tendency of spherical domes. So, and also revealed the geometrical principles behind the configuration of this space. And at the base of that, you recognize now we have some very large pendentives that ultimately discharge the vertical loads on some very large piers. Now, this is a space that it's overall almost 60 meters in height from the bottom, and a significant span that it's on the order of 35 meters at the top. So the configuration we're discussing here is a very large dome at the top, but then 4 pendentives that will discharge onto these very large piers you can see in these 4 locations. On top of that, Hagia Sophia has 2 hemicycles, or another 2 semi-domes that sort of protect and absorb some of the thrusts of the dome. And there's a series of buttresses as well that run on the opposite direction that likewise sort of contain all these massive forces coming from the top. Now again, if you look at the roof, you see this is a picture of the dome. This is the central dome here, and one of the semicircular domes on the side. And you can see how here there's a series of arches that are buttressed with some infills that sit in between the openings of the clerestory that allows some light in, and sort of gives this wonderful impression that the dome might be almost lifting as a result of the light and the contrast, but it's certainly not. There's a lot of solid support there in order to prevent this sort of bursting effect, and transferring this down onto the pendentives, and which are in these areas here, but also transferring these loads onto some giant arches that span from connect the 4 piers. And so here the dome sort of spreads its loads through these giant arches. Then the arches again take these loads down to these massive piers, and some of the thrust is absorbed by the hemicycles along one axis, and on the other axis it's somehow contained by the buttresses. Now, what is interesting about Hagia Sophia is, as much as it is a wonderful piece of architecture and construction that still survives, you should know that this building was designed initially in a different way, and it was designed with a segmental dome, so not so much like the Pantheon, but rather like just as a portion of a spherical dome. And you can see what it is according to the authority on this building, which is Roland Mainston. You can see how the initial intent or the initial plan of the dome might have been a much lower profile. Now, this lower profile is actually more problematic than a higher one, because it generates horizontal thrust that are more pronounced. So in other words, the component of discharge of gravity loads in a horizontal section, it's higher than for a dome that has a semicircular profile that tends to come down in a more vertical way. So here the component of horizontal thrust is less, for example, than the one that is horizontal, where in this case it's almost equal, right? So you have both horizontal and vertical components of loads that are very high. In this case it has been reduced, but the vertical component is high, but the vertical loads are not a problem in masonry, because masonry resists well compressive stresses. Now, this is proven also by the fact that there has been some archaeological studies that have brought to the fore the fact that the dome in fact was built in different stages. It also collapsed as a result of an earthquake around in the 6th century, and it was rebuilt according to that. However, so there was some inherent faults in the design somehow came to destabilize and create problems on the building even earlier than the famous earthquake event. And this is the final configuration of Hagia Sophia today, where you see again the 4 pendentives here, or 2 of them shown in this section. They're discharging onto these piers that are in this location. You can see here the giant arches that are connecting one pier to the next. And then you have the weight of buttresses here that is somehow reducing again this component of vertical or horizontal shift and thrust onto a resultant force that is more vertical than it would be otherwise. And here is an example of what the effect of this fairly troubled building has had over time, where you have a situation of a dome that is being pushing sideways onto these giant arches, and you can see how some of this deformation have remained almost permanently in the building, including to the extent that some of the columns are notoriously leaning, some columns in the gallery. And again, here is a view from looking up, where you can admire how this dome was executed with the full pendenties, the semicircular, smaller domes along, the one of the axes, and then a series of arches that somehow connect all together and revolve around, but leaving a clerestory that allows light in. So when the light comes through, it gives this sort of immaterial sense of the dome almost floating above the pendentives. Although it is not, as we saw, there's so much more behind that prevents that to be a problem. Now, Hagia Sophia, of course, is the most renowned example of Byzantine architecture, but it's important to understand that significant example is not a standalone phenomenon. And in fact, there's many other examples of churches, not necessarily so big and magnificent, that have they survive and they've often been converted to mosques, but they still show what the initial intent was, and they also reveal some of the characteristic construction systems of the time. Now, the Byzantium was an offshoot of Roman culture initially, and so it adopted some of the most important techniques of Roman construction, in particular brick construction, which was very useful in creating domes in particular, and complex configurations overhead, because bricks have a certain amount of tolerance that can be inbuilt into the process. So what the Byzantine used was bricks, and often they used an abundant use of mortar, not of concrete, so not pozzolanic mortar, but lime mortar. The bricks were kiln dried, and the characteristic also of this architecture was then a finish of rendering that was the base for mosaic decoration. So there was a substrate that allowed to, and a technique of construction that was not necessarily new, but it was used in a different way. It was used to give scope for spaces overhead that were able to span, reusing the principles of geometry of semicircular arches, barrow vaults, and spherical domes, and then having this additional ability to cover up or finish the surfaces by using mosaics as a way to tell stories and to decorate the building inside. And so you can see how some of these buildings, when they've lost the mosaics, they reveal this brick construction with very large gaps of mortar infill. And other times you can see how brick construction itself is not necessarily the sharpest, but it is somehow that's what makes this the advantage of this technique, that it can be finished later on with plaster. Now, this is not to say that there was not some consistency in construction during this time, and there was in fact some recurrent methods of wall construction which borrowed, yes, from the opus statue, but they also borrowed from the Roman technique of the opus mixtum, if you recall. So here the idea is to have, in the opus mixtum, is to alternate brick construction with masonry construction, with bricks used to create some bands and some sort of opportunity to strengthen the horizontality of walls. And Byzantine used this technique as known as the Constantinopolitan band construction, when you have masonry courses intermitted by several courses of bricks, and you find that often there are some holes cut into these bricks for inserting put logs, or the opportunity to insert progressively as the construction proceeds in some posts to support a scaffold. And another technique was then the so-called recessed brick, very common too, where again you see very likely used in this location here, where you have very large mortar joints apparently, but actually looking closer you find that there is a brick infill behind. So this is the technique of construction as it might have happened in many circumstances. So this ability of using smaller elements, not necessarily large stones, not precisely cut stones, and pick up any irregularities and distributes and somehow rectify any imperfections with an abundant use of mortar. Lime mortar, again, not pozzolanic mortar. Lime mortar often used in this case as a brick infill, again a remnant of the opus cementitium but without the benefit of the pozzolana itself. And then put logs that are used to put some transverse supports for scaffolds. And so it is a method of construction that allows to go up vertically, but it also allows to handle materials using smaller elements like brick, the ingredients of mortar, and some rubble. Now, I'll mention also about the recessed brick construction. Now, recessed brick construction is the one that is characteristic of very large external mortar joints, but behind these very large mortar gaps, there is often another brick that is being pushed in, recessed in, and then it's finished sort of so that it doesn't show up anymore, and only every second course in this case is revealed on the facing. Sometimes there could have been another approach with in between the mortar joints there is some infill of broken bricks or that are used somehow to spread the joints further. And then behind this brick construction, again, bit of opus testatium that is evolved. You still have some rubble of fragments, not necessarily of high quality, not materials that are useful for finish, but that are inserted in the wall thickness. And here are some examples how these techniques of construction then is also married with the semicircular arch that was so popular with the Romans. Again, here you see the same technique of recessed bricks with large bands of mortar and bricks that sort of are recessed back and they're not visible anymore unless you have situations like this where buildings are ruined and some of these traces and methods of layering become apparent. And then put log construction that we use to insert scaffolds. Now, the influences of Byzantium, as we said, spread to the west, and they spread particularly in northern Italy, but not only there, also along the coast, the Dalmatian coast, along the Adriatic Sea, on the opposite side of Italy, along Montenegro or Slovenia, Croatia, and so forth. And so the influence of Byzantium was significant, particularly in a city of Ravenna. Now, Ravenna was a city, well, still is an Italian city, in the northern east coast of the peninsula, and it was an important city because once the Western Roman Empire was sacked by the Visigoths, and in the 5th century, the emperor of the time just shifted the capital of the Western Empire temporarily in Ravenna. So, for obvious reasons of strategy, in order to be closer to the east, and by having a route of connection through the Adriatic Sea that allowed to reach Byzantium, or allowed to reach Byzantium also by land, in a much easier way than having to cross the mountains of the center part of the peninsula. So this strategic position of the city of Ravenna is somehow facilitated the flourishing of architecture that was in connection and influenced directly by Byzantine influence. And so this is evident, for example, San Vitale. San Vitale is an octagonal church that was based very much on the from a layout point of view, on the Temple of Minerva Medica. It still was survives as a ruin in Rome. And you can see here the method of construction of bricks and fairly large, generous mortar joints. And again, the approach, in this case, of an octagonal plan and surmounted by a semicircular dome, and the use of mosaics inside, as well as the use of pots in the dome, a technique that was often used by Romans. Again, here's another example existing in Ravenna, where the Orthodox baptistry, or the baptistry of Neon, where you see the almost austere brick construction, very simple, but then that's giving the bones and the structure to this domed spaces that are embellished by mosaics inside. And again, here you find this particular building, there is a use of a series of pots here that are interlocking, and this is the so-called tubi fitili, or tubes of terracotta that the Romans used for pipes, that have been recycled or reused in this very innovative way in order to have a lightweight vault of terracotta that is finished also with a mosaic. Now, the influences of Byzantium also are most evident in Venice, and Venice, not far from Ravenna, a bit further up north, and a city that would flourish particularly in the centuries that followed the flourishing of Ravenna, but the Byzantine influence in Venice are most obvious, particularly in San Marco, the cathedral of the city. Where you can see here a clear, central plan arrangement, a central dome surrounded by smaller domes around, and semicircular domes again sitting on the pendentives and then discharging onto these piers that you can see here in plan. These are the pendentives and how they discharge onto these 4 piers that are domed themselves on in between at the top, at the ground floor. Now, the older footprint is clearly a Greek cross here, and you find that there's some more construction, the narthex, which surrounds the cathedral with this very glittering architecture that was developed later. But if you look closely behind, the inevitable, rich decoration of the cathedral, you can see there's some austere brick construction sections. You can see how the domes are sitting on drums or brick construction. You can recognize the perfectly semicircular openings, and whereas nearby you start to see Palazzo Ducale that has some Gothic influence of a later time. And so behind this facade that evolved in time, you're able to recognize the old austere architecture that we can observe in Ravenna. Bricks, semicircular arch construction, and again some obvious connections. For example, in this case, that apparently it is argued that San Marco was inspired by this church in Istanbul, Constantinople, San Xavier in the Cora, almost contemporary. You can see this link here between the fenestrations here, very, very Italian apart. So Byzantine construction was the base of what would then become also the Romanesque construction of medieval time. And Romanesque construction, not Roman, it is a type of construction, and again took the techniques of construction in Rome, but adapted it to ecclesiastical architecture. And it did so by using again the semicircular arch as the generating device for which vaults and domes were created. Now, before touching on the groin vaults, which are the most characteristic, perhaps, method of vaulting and construction of the Romanesque period, we can start by looking again at the Barra vault. Now, the Barra vault, as we said, is a semicircular arch that has been extruded in one direction, and we saw again the Colosseum as the perfect playground in which all different kinds of barra vaults were developed and used by the Romans. But as we said as well, the barra vault generates a plane of thrust. So in other words, a series of horizontal and vertical discharge points where the horizontal component can be significant and needs to be absorbed very often by having buttressing or very thick walls on the side of a vault. That is the structural problem of the barrow vault, but there is another problem, which is the construction problem of the barrow vault. Now, if you imagine you have to build a barrow vault like this, well, you would probably clearly imagine that you would need some form of false work, also known as centering, to make sure that you maintain the same profile as you proceed. Now, centering will be very difficult to achieve and control for a number of reasons. If you were to build this vault all in one go, in order to maintain its consistency of profile, it might be convenient, for example, to set up a series of centerings all in one go and then proceed to vault the space above. But this is obviously very difficult to achieve, and so you'll find that more practically it is better to have a series of centerings, perhaps in bays, and then proceeds, for example, by building one section of the vault, and then moving these frames to the next bay and continue in that fashion. So in other words, you can proceed in sections like you would do in construction today, or by staging it. And in doing so, in order to interlock one vault to the next, it will be convenient to insert some bands or some lower semicircular arches that can be used to disguise any joints that might occur from one stage of construction to the next. And so this is the technique that ultimately will open up to the methods of construction that are also characteristic of Gothic. And it's the idea that you build first a frame or a framework where you define the geometry or the key geometrical controlling surfaces or lines from which you then infill the spaces in between. So a groin vault, as we saw, is a barrow vault, or part of a barrow vault that is somehow intersected by another barrow vault that is running in the orthogonal direction of the first one. Now, if you have a series of banded barrow vaults and then you put a series of banded barrow vaults in the other direction, you obtain what is an open groin vault, which is characteristic of ecclesiastical architecture of the Middle Ages. And so, first you would imagine this scenario where you can build a series of arches that are simply semicircular arches in one direction, and then from the same piers you build a series of arches in the other direction. Now, this would have some benefits, that particularly when four arches sort of come together at a connection point, you don't need to have any major concerns for picking up the thrusts in a horizontal direction, but everything will be channeled down to the piers. But there's some catch in this problem, and this is a geometrical problem that also affects the construction. If you have two surfaces that are circular and you intersect them, you obtain a series of surfaces at the intersection that are known as groins, hence the name of groin vault. And these groins are not circular, but they're elliptical. And so, hence, again, if we use brick, for example, we might find that it's a bit easier to control the geometrical, the inevitable irregularities that are much harder to control for an elliptical centering that you would have in a circular format. And this somehow also brings further the idea of using bricks as the main method of construction during Romanesque as well as from the Byzantine period. Now, of course, there's an opportunity to use stone, and there are some examples that show that, but you can see here from these pictures where on the one end you have the advantage of having a series of groin vaults that can discharge only vertical loads, particularly in the central bays, and take care of horizontal thrusts on the end bays. So there's certainly an advantage here that you're able to open the space more. But you can imagine here the work of stone cutting that is required in order to interface all these groins together. So there's another problem to this, which is also the management of centering or false work or forms that can be reused progressively. So this is an example of what you need to do if you have to build a barrow vault. This is a modern example taken from happening these days with concrete. And you can see how if you're willing to achieve a simple barrow vault, you know it's very simple just to set up a centering system, which is half a circle supported on some struts. And in this case, there's a series, or you can recognize here, is a series of segmental profiles that are overlapping to one another, and they're kept together by these transverse boards. So what will happen here once the concrete is poured, and then of course there's a series of lagging or boards that give the final profile, so concrete doesn't filter through. You can recognize how there's a series of these supports in place, and the space below so people can actually walk. Now, when the weight of the vault starts to apply itself on the centering, what happens is that this pushes down, and the effect, and this might push out, and it might actually make it almost impossible to remove the centering if it's done in one piece. So one thing that it was very important to control in barrow vaults or any kind of vaults was always the ability to remove the centering, possibly by recovering them and reusing them a second time around without too much damage. And you can see how here in these modern examples this would be achieved, for example, by removing these diagonals first and then lowering these separate sections of the of segmented sections that give the shape to the semicircular profile of the vault. And then by doing so, you're able to rebuild and proceed further. So the centering techniques were essential to achieve these barrow vaults, but also the groin vaults. But they relied always on some methods of construction that they needed to be simple enough to be set up geometrically. Now, of course, a circle is very simple to set up. All you need is a string and a fixed point, stretching a string or a stick and of the same length, and then rotating it at a pivot point allows you to draw a circle. Much harder is to draw instead an elliptical shape. And in that process, there was therefore an ability, for example, like in this reconstruction here, to have some segmental sections sitting on a springing point, and then an A-frame in between them. And this A-frame was able to be lowered separately by the other two, so that once the vault is complete and it starts to put pressure at the key there is the ability to slide down and remove a central section, and then the other sections can simply rotate and be folded away. And so obviously there would have been systems of this kind where there was some props of timber and the ability to wedge in position these different frames together. Another technique that would have been used very likely in those days would have been to have, instead of having an A-frame, perhaps a larger section profile like this on both sides, and a central block just under the key of the vault, kept in place with a wedging of another timber block to prevent this to move temporarily. Then this block will be knocked out once the vault is completed, and again the two centering frames can be removed and reused and built again in sections. Therefore, there's this characteristic method of construction using very simple geometrical false work, semicircular, in sections, in bays, and then using only simple shapes of semicircular profile to create surfaces that can also be complex, like in this case. So if you're trying to create a groin vault, you can have, for example, 3 centering frames all aligned, and then perhaps put lagging boards over it first, and then create instead the intersection, rather than cutting it through the boards, by putting another series of centering frames that reduce themselves progressively, and so these are still it's a portion of a barrel vault that it's triangular in two directions, and then these boards would infill and connect to the other barrel vault. Then the vault will be completed over that, and then the process can be, again, the centers will be removed and reused. Now, as we said, there is a problem with this system, and the fundamental problem of the groin vault is that the rib that is generated by two semicircular profiles or semi-cylindrical shapes is that the intersection generates a diagonal rib, like here, which is elliptical. And an ellipse is not an easy surface to control. So you find that the next step of evolution in these methods of construction was to not use necessarily the diagonals as an elliptical shape, but rather to build the diagonals, also known as the ribs of the groins of the vaults, but build them with semicircular arches. So in doing so, imagine now if you have a situation when you have 4 columns, and instead of starting from the transverse ribs, which are the ones that span from over the main nave of our church, and the wall ribs on the side, if instead of starting from those edges of the bay, you will start from 2 diagonal ribs, and they are circular in profile. So what you will be doing, you'll be recreating the conditions of the circular dome, like the Pantheon or Hagia Sophia. And so if you have 2 ribs that are actually perfectly semicircular and they sort of intersect one another, obviously there will be the problem that the arches that define the transverse and the wall ribs would not be as high as the diagonal ribs, because the diagonal will be larger in diameter than the transverse and the wall sides. And so this creates 2 opportunities. One is to create a vault that is somehow lower at the sides of on the sides of the nave or in the transverse rib direction, or it creates the opportunity to raise the springing point of the transverse and wall ribs by creating what is known as a stilt. So in other words, the apex of all these profiles on the edge of the groin vaults are at the same level, and there's a section at the base of the shorter arches that are sort of raising them up so that they can spring at a highest point. But also this opens up an opportunity, and the opportunity is that the 2 ribs intersecting at 45 degrees can generate what is known as a domed groin vault. So in other words, we can regenerate the same space of a dome in over a vault. Now this is easier to manage from a setting up of the groins, but it creates other problems when it comes about creating, for example, an arrangement of boards and legging that can be achieved successfully. So for example, if this is a rib or a groin that it's semicircular in this position, and this is the type of arrangement that we are trying to recreate, you will see that there is a need to have a series of centering frames or false work ribs that are created in order to follow a spherical surface. So you can see how all these complexities somehow create the basis for 2 things. That without having a good control of stereotomy, which is a technique for cutting stone using very rigorous geometrical principles that was not available in the medieval times. You can see how inevitably these techniques lead to the use of bricks rather than exposed masonry, and bricks that are ultimately filled with plaster. You can also see how there is a tendency here logically to start by building the ribs rather than the arches on the nave and proceeds from the ribs onwards. So all these things come together just by observing some buildings of that time. So for example, let's go now to Milan. Milan, northern Italy, one of the cities that was, again, that prospered after the fall of the Roman Empire, and that had significant influences from Byzantium to much extent. But in Milan, towards 1100, this church was built, the Church of Sant'Ambrosio, a very important center for the city, charged of many historical values still today. And this church was built, it's recognized by many as a perfect example of Romanesque architecture. Now, Romanesque here, because again, it's using the Roman sort of ingredients of brick construction and semicircular arches. And you can see here the church is somehow embedded into a portico, a courtyard that leads into the church. In fact, it's a very special space if you enter it. It's a church in the middle of a city, but sort of surrounded by this cloister feeling that almost puts you in a different space and mindset when you walk through, still today. And this church is somehow uses some of those it shows some of the techniques that were used to overcome these problems of the groin vaults. So you can see here in the portico, like you have perfectly semicircular arches here, and that are spanning in one direction and the other. So there's some ribs of brick construction that are apparent also in the orthogonal direction. You can see the wall rib here at the edge, and you can see there is a groin profile here that is coming together. But what is characteristic of these groins is that somehow they disappear towards the top, showing that actually this is a domed vault profile. So it's a semi-spherical dome that it's using circular ribs as a setup points initially. And you can see here how the groins are somehow more evident at the base, but they somehow disappear because you have here a semicircular profile that is extruded in one direction and the other, but the rib itself here are both semicircular, so it's a sphere that is intersecting two cylinders on both sides that creates this very, sort of semi-concealed groin system. And you can see here the ribs that are clearly pronounced that lead to the entrance of the church. Inside the church, this is the plan of the church. You were looking down here on this side, on the left hand side there of the portico. Once inside the church, you find that there's this very large 2-story high loggia that lets light in. There's a different type of construction, but still using this principle. You have a ribbed dome here with ribs of bricks, which is semicircular. You recognize now here again a semicircular arch, in this case in stone. You can see the piers, how it discharges down, and you can see how the two ribs connect to each other. These are semicircles, and this is another semicircle, but the apex of this vault is much higher than the crown of this arch below. And so what is generated here is a domed again profile, where you have the ability to control the construction by having a rib that defines the geometry. And then you can see here the side arch here. So this vault here would then discharge at the back into the gallery of the matroneo, as called in Italian, which conceals the walls that discharge from the top. You can see there is no windows coming here in this side, very different, and a problem that will be solved by Gothic. And you can see there's light coming in from the dome and light coming from the back, from the loggia at the front. So if you look at a section of this building, you now recognize this method of covering, where you have ribs of semicircular arches and vaults that are somehow springing from this point and reaching out these higher ribs and then discharging through the gallery here with these buttresses. So the lateral loads of vaults are absorbed by the piers and by a buttress system behind. And then there's a dome at the top, which is somehow completing the transept and just completing the church on the opposite side. You can see here a view of the dome, and you can see how these arches all spring from the same point. So there's a common spring here, meaning that these will be semicircular ribs that are of bricks. They will be taller, and the stone arches that are in the transverse and the wall ribs are smaller, but they all come together by using a vault that is hemispherical. And this is the vault itself over the intersection of the transept and the nave, where you have at the very top, of course, a mosaic of the saint, St. Ambrose in this case, that has been used at the crown. And you can see here how the dome is resolved in an octagonal way by using this sort of corbelled pendentive, that it's again reusing arches to somehow reduce the springing point of the dome above. And the dome is composed by groins and sections that are sections of a sphere that are somehow all connected together and in this octagonal arrangement. So I'll conclude here with this one. This is an important step to understand in order to discover then what's going to come next. And what comes next is, of course, the Gothic. So in this discussion here, hopefully we've understood some of the basic principles of vaulting and some of the main challenges that surround this form of construction that has had so much influence and still, I believe, influences architecture today. So I'll leave you with this one here, and I hope you're going to have a good day.